Sketch the graph for the function f of x equals x minus sine x by determining the parts a through I. F of x equals x, a polynomial term. The domain will be all real numbers. Minus sine x, a trig function with no denominator. The domain will also be all real numbers. So for part A, the domain is collectively all real numbers, or negative infinity to positive infinity. Trig functions have a tendency to have an infinite number of intervals of trend and intervals of concavity throughout their entire domain. But nicely, sine x is 2 pi periodic, which means that it repeats itself every 2 pi radians. So instead of working on the entire domain of negative infinity to positive infinity, we can instead work on the unit circle interval, which begins at 0 and includes it, square bracket, up to 2 pi. Does not include it, round bracket, because 2 pi is the same point as 0 on the unit circle. Find the results on the unit circle interval, and we can extend those results to the entire domain using the 2 pi periodic nature of sine x. For part B, we want to determine if there is any symmetry. This is done by evaluating f of negative x and comparing it to the original function f of x. F of x is made up of an odd power of x, this is an implied first power, which has origin or odd symmetry, and sine x, which also has origin or odd symmetry. So overall, it should have origin or odd symmetry. F of negative x is negative x minus sine of negative x. So that is negative x. Sine of negative x has an identity that it equals negative sine of x. The double negative will make positive sine of x. We can factor a negative out of here, and that will leave behind a positive x and a minus sine of x. Comparing this result to the original, it is exactly the same, except has a negative factored out in front of it, which means that f of negative x equals exactly negative f of x. And this is the condition needed to have origin, also known as odd symmetry. This means that the graph will be its own mirror image over the y-axis followed by the x-axis. We will be sure that that is the case. For part C, we want to determine the y-intercept. This is the point where the graph crosses the y-axis, defined by x equals 0. We can find the corresponding y-coordinate by plugging the x-coordinate back into the original function, so y equals f of 0, which is 0 minus sine of 0. Sine of 0 is 0. 0 minus 0 equals 0. We have an x-coordinate of 0. We found a corresponding y-coordinate also of 0. For part D, we want to determine the x-intercepts. These are the points where the graph crosses the x-axis, defined by y equals 0. Y, which is f of x, will be set to be as 0, and we can solve for all x's that make this true. So 0 equals x minus sine x. We can add sine x to both sides. So sine x equals x. This cannot directly be solved because x is stuck inside of a trig function on the left and a power function on the right. But we can solve it by inspection, because sine of 0 equals 0. So x equals 0 at the very least solves this. X is a growing function. Sine x is an oscillating function. And therefore they will cross each other this one time only. There are no other x-intercepts. We had a y-coordinate of 0. We found a corresponding x-coordinate of 0. So 0, 0 is the only x-intercept. For part E, we want to determine any vertical asymptotes. F of x is a polynomial term and a trig function with no denominator. Therefore, there will be none. For part F, we want to determine if there are any holes in the graph. F of x has no denominator, so there will be none. For part G, we want to determine any end behavior, horizontal asymptotes or slant asymptotes. F of x is a polynomial term and a trig function with no denominator, so it will not have horizontal asymptotes or slant asymptotes. But because of the polynomial term, it will have left end and right end behaviors of positive infinity or negative infinity. We can determine the left end behavior by taking the limit as x approaches negative infinity of the function. Only the highest power term will matter here. Sine x is an oscillating function, so only the x will matter. Plugging negative infinity in will give negative infinity. We can determine the right end behavior by taking the limit as x approaches positive infinity of the function. Again, only the highest power term matters here. Sine x is an oscillating function, so only x matters. Plugging in positive infinity will give positive infinity. For part H, we want to determine the intervals of trend, relative maxima, relative minima, plateaus, and cliffs. All of this involves the first derivative, f prime of x. We can take this right from f of x. Derivative of x is 1, minus derivative of sine x is cosine x. We can set the numerator equal to 0 and the denominator, if there is one, also equal to 0 and solve for all x's. We can add cosine x to both sides. So 1 equals cosine x. There's an infinite number of places where cosine x equals 1 on the entire domain of negative infinity to positive infinity. But on the unit circle interval, there is only one place where this occurs. It is x equals 0. It will happen again at x equals 2 pi, but 2 pi is not included on the unit circle interval. So x equals 0 is the only critical number. We can now draw a unit circle interval line, a line representing the unit circle interval. It begins at 0. It includes 0 because of the square bracket, but we found x equals 0 to be a critical number, and we are removing it from the unit circle interval, so it'll be a round bracket there. It does not include 2 pi, so it'll be a round bracket there. We put any other critical numbers on here. There are no other critical numbers, so there is only a single interval to test, and that means that the function will have the same trend on each of the intervals over the entire domain. We can pick a test value between 0 and 2 pi. Pi works. We can test the trend by plugging the test value into the first derivative. We only care whether it's positive or negative here. Cosine of pi is -1. 1 minus a -1 is 1 plus 1. That will be a positive number. We have a positive first derivative. This corresponds to an increasing trend. We have a critical number of x equals 0 here, right at the critical number of x equals 0, which is the left endpoint. We have a trend on the left side because of the 2 pi periodic nature of sine x. This trend will also be happening over here to the left of 0. So to the left of 0, we have a trend of increasing. To the right of 0, we have a trend also increasing. X equals 0 is a critical number, and the trend is not changing. It's increasing on both sides. That will make x equals 0, since it came from the numerator of the derivative, be a plateau. So we will have a plateau at an x-coordinate of 0 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of 0, which is 0 minus the sine of 0. Sine of 0 is 0. 0 minus 0 equals 0. So we have a corresponding y-coordinate of 0. We can now extend this result to the entire domain of negative infinity to positive infinity using the 2 pi periodic nature of sine x. To each x value, we can add the period 2 pi times n, an integer. For the plateau, we have the x-coordinate is an x value every time. The y-coordinate, because the function up here is x combined with the trig function, y, which is f of x, is also equal to x, so it is also an x value. So to the y-coordinate of the plateau, we can also add the period 2 pi times n, an integer. By doing this, we will find the location of the infinite number of plateaus. It will be 0 plus 2 pi n, which is 2 pi n, and then 0 also added because y f of x equals x, so y is also an x value, combined with a trig function. 0 plus 2 pi n. There's the location of the infinite number of plateaus. Here, n equals any integer. It can be a positive integer. It can be a negative integer. It can also be 0. N equals 0 will give the 0, 0 plateau that we found on the unit circle interval. N equals any other integer will give all other plateaus. For part I, we want to determine the intervals of concavity and any inflection points. We will need the second derivative for this. We can take the second derivative directly from the first derivative. Derivative of 1 is a 0, minus derivative of cosine x is negative sine x. We will have a double negative. That will give a positive sine x. We can now set the numerator equal to 0, the denominator, if there is one, also equal to 0, solve for all x's. Sine x equals 0 an infinite number of places throughout the entire domain of negative infinity to positive infinity. But on the unit circle interval, it happens at x equals 0, and again at x equals pi. It will happen again at x equals 2 pi, but that is not on the unit circle interval since it doesn't include it. We can now draw a unit circle interval line. It includes the 0, but we just found x equals 0 to be a candidate number. So we remove it, and there will be round bracket. 2 pi already isn't included. And we can put any other candidate numbers on here. We found x equals pi, the only other candidate number. This splits the unit circle interval into 2 separate intervals. We can test the concavity on each of the intervals by picking a test value. The first interval, 0 to pi, we can pick pi over 2. The second interval, pi to 2 pi, we can pick 3 pi over 2. And we can test the concavity by plugging the test values into the second derivative. We only care whether it is positive or negative. Plugging pi over 2 in, the sine of pi over 2 is a positive 1. We have a positive second derivative. This corresponds to concave up. Plugging in the test value of 3 pi over 2 into the second derivative, the sine of 3 pi over 2 is a negative 1. It's a negative. We have a negative second derivative. This corresponds to concave down. Right at the candidate number of x equals 0, which is the left endpoint, because of the 2 pi periodic nature of sine x, this concave down interval will also exist over here to the left of it. We have the concavity changing from concave down to concave up. So x equals 0 will be an inflection point. So we have an inflection point at an x-coordinate of 0 and a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of 0, which is 0 minus sine 0. Sine of 0 is a 0. 0 minus 0 is 0. So we have an inflection point at 0, 0. We can extend this to the entire domain using the 2 pi periodic nature of sine x. We can add to each x value the period 2 pi times n, an integer. The x-coordinate is definitely an x value. The y-coordinate, again, because f of x equals x, combined with a trig function, will also be an x value. So we'll add 2 pi n to each of those. And that will give an infinite number of inflection points. They will be 2 pi n and, again, 2 pi n. Where n, once again, is any integer. It can be a positive integer, it can be a negative integer, it can be a 0. Right at the candidate number of x equals pi, again, we have the concavity changing from concave up to concave down. So x equals pi is also going to be an inflection point. We have an x-coordinate of pi, and we have a corresponding y-coordinate that can be found by plugging the x-coordinate into the original function. So y equals f of pi, which is pi minus the sine of pi, which is pi minus the sine of pi is a 0. Pi minus 0 is pi. So we have a corresponding y-coordinate of pi. We can extend this to the entire domain of negative infinity to positive infinity by using the 2 pi periodic nature of sine x. We can add to each of the x values the period 2 pi times n, an integer. The x-coordinate is definitely an x value, and the y-coordinate, again, because f of x is x, combined with a trig function, is also an x value. So we can add 2 pi n to each of those. So we'll have pi plus 2 pi n, comma, pi plus 2 pi n, where n is any integer. It can be a positive integer, a negative integer, or a 0. N equals 0 will give the inflection point pi, comma, pi. We can now graph the function. We can draw the vertical axis. We can draw the horizontal axis. We have the domain as negative infinity to positive infinity, so it will exist over all x values. We have that it should be showing origin or odd symmetry, which means that the graph will be its own mirror image over the y-axis followed by the x-axis. We'll be sure that it follows that. That means that whatever we see in the first quadrant, we will see its reflection over the y-axis and then reflected over the x-axis. So we will see it in the third quadrant as flipped left, right, and flipped up, down. And whatever we see in the fourth quadrant, we will see flipped over the y-axis and x-axis. So again, left, right, and up, down in the second quadrant. So we'll make sure that that is the case. We have a y-intercept of the origin, so it definitely crosses right here. We have an x-intercept that is also just the origin. We have left-end behavior of negative infinity and right-end behavior of positive infinity. Left-end behavior of negative infinity means that it'll be down here for the left end, and right-end behavior of positive infinity means that it'll be up here on the right end. So we'll be sure that it follows all of that. Now, right at the origin, it has a plateau at the 0, 0, so we'll draw a plateau look there, which looks something to this effect. We can label that. That's going to be 0, 0. We have, in general, plateaus occurring at 2 pi n, comma 2 pi n. If n is a 0, that'll be 0, 0. If n is a 1, that'll be 2 pi, comma 2 pi. So there will be another one somewhere about here, taking a similar kind of shape to it. We can label that as 2 pi, comma 2 pi. We'll have another one somewhere up here when n equals 2. That will be 4 pi, comma 4 pi, and on like that. We can also pick the integer to be a negative number, so if n equals -1, we'll have one at -2 pi, -2 pi, so it'll be somewhere about right here. So we can label that -2 pi, -2 pi. If n equals -2, we'll have one at -4 pi, -4 pi, so that'll be somewhere about right here. And on and on. Now, we also have an inflection point at 0, 0. Well, 0, 0 is a plateau, and plateaus are always inflection points, so no surprise there. As a matter of fact, the general inflection point of 2 pi n, 2 pi n is just the plateau points that we've already graphed on there. So that checks out. Those are certainly inflection points. The concavity change is always around a plateau. Each of those have a concave down on their left and a concave up on their right. But we also have an inflection point occurring at pi, comma pi. That will be somewhere about right here. We can label that as pi, comma pi. And on the left of the pi, comma pi, it should be concave up. That means it's curving up, and that's happening right here. It's certainly curving up. And then on the right, it needs to be curving down or concave down. So it's definitely following that. In general, we have inflection points at pi plus 2 pi n, comma pi plus 2 pi n. If n equals 0, that's the pi, comma pi we just graphed. If n equals 1, that will be pi plus 2 pi. It'll be 3 pi, comma 3 pi. That will be right here. And so we can label that as 3 pi, comma 3 pi. And it's concave up on the left and concave down on the right. It's curving up on the left and curving down on the right. If n equals -1, we'll have an inflection point at pi plus 2 pi times -1, pi minus 2 pi, which is negative pi, comma negative pi. That'll be right here. So we can label that as negative pi, comma negative pi. And again, it'll be concave up on the left side of it and concave down on the right side of it. And if n equals 2, -2, we'll have pi plus 2 pi times -2, pi minus 4 pi, which is -3 pi, comma -3 pi. That'll be right here. We can label that as -3 pi, comma -3 pi. And that will be concave up on the left and concave down on the right as the other inflection point. And it is showing the origin or odd symmetry, because this portion of the graph, if it were to be reflected or the mirror image across the y-axis, and then reflected or the mirror image across the x-axis, it will completely overlap on itself in the third quadrant. So it is following that origin or odd symmetry. Also notice that it does have the left end behavior of negative infinity and the right end behavior of positive infinity, so it is following the end behaviors that it should be. So everything is checking out here. It is a 2-pi periodic function. It's oscillating, and it's following along the y equals x line as it oscillates there. This is, overall, the graph of f of x.